Okay, so with our related rates, it's just making use of our chain rule. So invariably with our related rates, we might have two variables basically that are related, as strange as it sounds, and are both changing over time. And I think the best way to consider that is looking at volume. If we look at volume in a cylinder or volume in any vessel, the volume of water, as we add water, the volume of water changes, but also the height of the water or the depth of the water is changing. In this cylinder, this cone question, as I add water, you can see that the radius of this cone is changing along with the depth of the cone, along with the volume of the water in the cone. So all three variables are changing and they're all related, hence a related rate. And it's normally our derivative and our chain rule that relates or ties these rates in together. So if we consider our cone here, if we look at the actual cone here, the triangle that we can create from the cone using the red triangle is just the dimensions of our cone. It's got a height of 30 centimetres, it's got a radius of 10 centimetres, so we can create this right angle triangle, all right? If we consider the volume of the water or the amount of water that's in the cone at any point in time, we've got a similar triangle, and it is similar in every sense. The proportion of the radius and the height are the same, the angle at the bottom of the triangle is the same, and hence we have similar figures. So using those similar figures, we can come up with a relationship between two of the variables, that is the height and the radius. So from similar figures, the radius over the height is the equivalent of 10 over 30, which means that r is equal to h on 3, or h is equal to 3r, depending upon which variable you want to eliminate. And by eliminating, if we consider the volume of the cone, the volume of a cone is 1/3 pi r squared h. So we have r in there, we have h in there. So typically when we differentiate, we only want to differentiate when there's one variable present. And we've spoken about how already the radius and the height are already related, so we can't differentiate that with both those variables present. So we do a substitution. I'm going to take h equal to 3r in this case, put the 3r in for h, and so in actual fact the volume could be expressed as pi r cubed, okay, just for this specific cone, all right? So if the volume is pi r cubed, the derivative of the volume with respect to r is 3 pi r squared. So there's my dV/dr. The question itself might typically give us one of the other rates. So we know from our chain rule dV/dt is equal to dV/dr dr dt. Okay, just from a chain rule, dV/dr we've just worked out, 3 pi r squared, dr dt would typically be given to us. So that's the process by which we might be able to tie in the rates of a scenario and work out how one variable is changing over time. Let's keep working through. So if we look at example 16, it's again a typical sort of example. We've got an ice block melting. It forms a circular puddle as they do, and the radius of the puddle increases at a steady rate of 3 centimetres per minute. So the radius is increasing centimetres per minute. So dr dt is 3 or 3 centimetres per minute. When the radius is 2, how is the area changing? So now I need a rule for the area. Fortunately, we've got a circular puddle, and the area of a circle is pi r squared. So if I work out dA/dr, I get 2 pi r. So now I've got area and radius are the variables with time that we're trying to tie together. So using my chain rule, dA/dt is equal to dA/dr dr dt. So which of those have I got? Well, I'm looking for dA/dt, the area increase. So I'm looking for dA/dt, dA/dr, 2 pi r, we've just worked that out there in purple, times dr dt, which was given to us at 3 centimetres per minute. So if I multiply that together, the rate that my area is increasing is given by 6 pi r. So the bigger the radius, which makes sense, the bigger the radius of my circle, the bigger the increase in the area of the circle. So in particular, if the radius is equal to 2, I substitute that in, I get 12 pi. That's an area. So my area is increasing at 12 pi centimetres squared per minute. Okay, so that's a typical example. If we keep moving on, we've got a rectangular block that's x by 5x centimetres in measurement. Express the total surface area in terms of x. So the surface area is the area of each of the faces. So I've got this long area here. In fact, I've got 4 of those side faces, and its dimensions are x by 5. So there's my x by 5 by 4. And then obviously I've got that front face, which is a square, and I've got this back face. So I've got 2 of those that are x by x. So I've got 2x squared, which means my total area adds up to 22x squared. So that's the area of my shape. All right. Calculate the rate of decrease of x when x is equal to 2. So we want the rate of change of the side length, the x dt. Okay, so what variables have I got? Well, I've got area in terms of x, which means dA dx. If I differentiate that, it's 44x. I've been given a value, 4 centimetres squared per minute. So that's the rate that the area is changing dA dt. So dA dt changing at 4 centimetres squared per minute. I'm going to put a negative because it's decreasing. So now dA dt is given by dA dx dx dt. All right, so dA dt was negative 4, dA dx we worked out to be 44x, and I'm looking for dx dt. Take the 44x across and cancel the 4s. I get negative 1 on 11x. That's the rate of change in my side length. All right. Specifically, I'm interested at x equal to 2, which means my side length dx dt is changing at a rate of negative 1 on 22 centimetres per second. So the negative implies it's decreasing, so you could argue it's asking for a rate of decrease. So you could possibly put just 1 on 22 centimetres per second. But if this was an exam, I'd be saying, you know, I'd probably specify it. It's decreasing at 1 on 22 centimetres per second. Yeah? Or we could say that the rate is changing at, and we'd put the negative sign. Okay, parametric equations is just an extension of that chain rule, and it's a related rate. What we've got, typically we've got an x coordinate and a y coordinate that are related by time. So if we've got our particle, yeah, and at a particular point in time, it's got that position or that coordinate, and then another point in time, it's got that coordinate. So they're related. Their positions are related typically by a Cartesian path, but it's also related over time. So again, dx dt, dy dx is dy dt, dt dx. So we're going to use integrate each component with respect to time to find out our gradient of the line or the rate of change of the line. It could be a speed. There's a range of different applications, isn't there? So x is equal to 16t squared, dx dt then is 32t, dy dt is 32. So dy dx is dy dt dt dx, which is equal to 32 times 1 over 32t, which just gives me 1 on t. So that's the gradient of the line at any point in time. Okay. Similarly, we've got a trig equation there. dx dt is 6 cos 3t, dy dt 6 sine 3t because the negatives cancel. So dy dx is dy dt dt dx, which is 6 sine 3t times 1 over 6 cos 3t. So my 6's cancel, I get sine over cos, which is tan, so I get tan 3t. All right. The one that we need to be a bit more complex is if we're looking for the second derivative. Okay, it's not differentiating each component twice and then joining them together. Let's have a look. X equal to t minus t cubed, y equal to t minus t squared. So dx dt, 1 minus 3t squared, dy dt, 1 minus 2t. So if I work out dy dx, I get 1 minus 2t times 1 over, so I get that 1 minus 2t over 1 minus 3t squared. Let's call that y dashed. So what I'm trying to do now is work out the derivative of y dashed with respect to x. Yeah, but y dash and x are both variables in t. So really what I'm looking for is the derivative of y dash with respect to x, which is derivative of y dash with respect to t times the derivative of t with respect to x. So I actually need to differentiate the first derivative again with respect to t. Okay, so work out dy dt, so I'm going to use a quotient rule here, the derivative of the top times the bottom minus derivative of the bottom times the top, all over the bottom squared. Join all those together, and it doesn't really simplify very nicely, but that's dy dash dt. And so to work out the second derivative, d squared y dx squared, I'm going to work out d squared y dt times dt dx. So there's my first derivative here, multiplied by 1 over dx dt, and all we really get is the increase the denominator by a power of 1 in the end. Okay, nothing really cancels out. So it's really just really important that if we're going to differentiate parametric equations twice to find a second derivative, it's not differentiate the components twice. Okay.